All right, let me check the audio before I start. I'm not getting a check on the audio here, apparently. Oh, here we go. So I'm going to assume we're going fine. Um, okay, so officially, I'm going to say we are in chapter 5. Um, Anything we didn't completely pick up out of 4, excuse me, is going to be, I mean, all this material goes forward anyway. So to get to 5, you have to have 4, and so on and so forth. So in 5, it's equilibrium of a rigid body. Um, Essentially, hang on. I'm sorry if I cough some, but I'm trying to get the. Okay. All right, I guess that's probably pretty good. So in here, it's basically you're going to come down to one simple concept. That's it right there. Some of the forces and the moments are all going to be equal to 0 such that the body doesn't move. And he's got some special blue blobs and things like that. You can do equilibrium in 2 and in 3 dimensions. And the next thing he talks about is free body diagrams. All a free body diagram is the replacement of a physical support like the roller here. If you, in your mind, you erase it and replace it with this, replaced with the force that the roller would put back on. Hence, the free body diagram concept is freeing the body of its supports and then figuring out what those supports are. When you do that, you've got a couple of different choices here. On the left end here, he says members, a pin, and some sleeves here that it fit in. Since it was pinned, it can take a force in the X direction and a force in the Y. If, however, it has a completely fixed support, it can also hold a moment. And that's why you get a moment here. Whereas in the pinned, you do not. It can simply rotate up and around that. Um, he has a list here, and it's hang on, try to get this back up. Okay. Um, you look at the different supporting methods, and you realize, okay, he's got a pinned thing at a wall here on the second one. Here he's got a cable. Cable can only be really in. I guess I gotta. Okay. A cable can only supply tension, so it can only pull towards here. Um, a weightless link, it can actually. Sorry, I'm having to um, deal with this cough at the same time. So in a link, like right here, you can supply it in compression or tension. If you have a roller, the ground can't exhibit a force perpendicular, or it can only have a perpendicular. It can't have the surface can't supply a force to this member here. This is a very common one. It's a rocker. This pin can move this way freely, but it cannot move towards the ground freely. So this is the force here. This is essentially like a roller, but this is what's used more often. We have a smooth, oh, okay. You have a smooth contact surface. You have this smooth pin in the slot, meaning the ground can supply force this way or this way on either end. And you have this sleeve, and this sleeve is kind of interesting. It's a smooth rod. It can basically, so what we're doing here is we're figuring out how the physical structure here relates to when you do the free body diagram, what type of force are you supposed to put in replacement of that? Okay, and you get rid of that. You have another one here. Pin or a hinge. This is a member that can slide up and down here, but cannot rotate in this direction. And then you get a complete fixed support. And he has some pictures of some examples of this. Here's a pin. There's a very common rocker system right there. You can find these fairly common in a housing structure like that or a building. You'll see more welded. In highway structures that the sun is going to sit on, you might need this thing to be able to slide because of the temperature change. In that case, the rocker would move because of the temperature change. Then you're looking at internal forces. And so what you're doing, internal forces are simply weights. They could be because of a magnetic field, but more often they're because of the center of the gravity of the weight and the structure there. So what you end up with is here he's got some beams, some trusses that are laid across the top, and the location of the little supports along there, certain distance A, B, and C. So you take a physical structure, you can redo it like this. Here's your center of gravity right there. Okay. And so let us move on and we'll get to a problem or two, but things are moving slow on the computer's front. Okay. I don't know why it's not paying attention to this side. I won't pay attention. There we go. Okay. I'm not sure what's going on. Okay, here we go. So essentially what he's doing to do this is he erases the brick wall, replaces it with the three forces that the brick wall would put back on the structure. And then he finds the forces there. Okay, I think I clicked 5-2. I'll double click it. I guess that's maybe what's required. I can see there's an attempt for a little circle to occur here. Okay. So in this particular structure, you can see there's a guy's foot right there pushing on this straight down 5 inches out. And so you can just basically remove the support right here, remove these two supports and replace them with their loads. So the left is not the free body, the right is the free body. And let's see. Each one of these looks or follows a similar. Okay, I'm trying to get it to go. All right, it finally went there. Okay, here he's got two big long tubes sitting right there. And of course, you could treat this little part right here as its support. And lo and behold, you take it off of its support, and this is what you get, a force here. This is for A reaction load here. So you're basically taking it away from taking it away from all of its supports. You're going through the process of finding it. Okay, let's go back. Let's go ahead and go. We'll solve some of these problems in a minute. Okay, double click maybe. So as we go through here, this is what you see as your forces, and your sum of the forces and your sum of the moments are all zero. That's all there is to this. You can do an alternate set, which is sum of the moments around a couple of spots. And so I'll let you look at those examples, and then in a minute I'm just going to go work one. There are examples in here. There's a whole bunch. Let's look at 2 and 3 force members, and then just start working some problems. There are plenty of examples. I'll let you look at all those. Usually, he has a video that goes with each one of those. So, 2 force member is something that looks like this. You got 2 forces here. This can't really set up. There's only one thing that can happen, and that's this, in which A right here, and B are pulling in directly equal and opposite locations. 2 forces on a body that's in equilibrium. That's all you're going to get. Then you can go in. Okay, well, 3 force members are something like this, where there is a common point somewhere, which you can sum a moment about. And so let's just go in and find problems. I'm going to go get a drink here real quick. All right, I'm back. Let me move this liquid to the other, and I'll pick a problem or two and start working them. I have no idea why exactly in class. All right. Okay. So let's see if I can roll down through this and pick a good problem. Okay. This is weird. I guess I have to use my finger. It won't let me use the... That seems pretty interesting. That seems pretty interesting. Here, we'll just do... Let's see if I can... I'll just... Okay, come on. New. Okay. Just going to drop this over into here. Now, you want to do a free body diagram of this. What we'll do is go back over to it. This time, we will do it in a free-formed. Tried to do a reasonable job of eliminating the supports, but okay, we'll just go underneath here. And start working it. Okay, looking back at the member, we realize this can take a vertical load, and then if you look at the thing, it can also take a load this way, which I'll call this AX and AY. This one can only take a load that direction and just call it B. However, this will be B cosine 30 and B sine 30. So now you got a couple of choices. You can do some of the moments. First thing I like to do is look for points that can help me here. I'm going to pick point B. Since it appears pretty close to the fact that these points almost line up, then I would think this X force would not supply a moment about B. And so that's the approach I'm going to take. And so essentially what that would be is you would have this force supplying a moment this way, which would be 4 now kilonewtons, and then 2 meters. Then I have this one applying a moment that way, which is minus AY times 6 and 2 is 8. So AY would have to be, move that to the other side, and you'd get AY is equal to 1. Now, could do things in a very interesting way. I could sum moments about A, or I could do something really strange. Let's try this for a strangity. Okay. Here's the way I'll have to do it. I'm going to shrink this down. First, I'm going to erase that red. I'm going to make this thing a little smaller. Move it to maybe right there. I'm going to bring out my ruler. And I'm going to sweep this here. Here, I tell you what. Let's not use that one. Let's use something like that one because it's a little... Okay, you got that one. Yeah. You got that one. So this one must... Yeah, I'm not sure I'm really getting it here, but I keep trying. This one has to be that. It says 38 degrees. So the approximate location of L is going to be such that this is going to be... Okay, so if it's 38 degrees. If I sweep it down, it's 38 degrees relative to that. Now, this is me putting a question mark because the first thing this has to work is it has to be everything to scale. I'm not sure that's the case, but here's the deal. I can sum the moments about L equal to 0. This is not going to produce a moment about L. This is not going to produce a moment about L. So this means that A can't produce a moment about L. So this is a 3/4 member. So we've got something like that, okay? If it were to scale, we can use this as a check back, and that's what I'm going to try to do here in a minute. Okay, so I'm going to look back at that in a minute, but right now I'm going to sum the moments about A, since I did it about B earlier. So now I'm summing the moments about A. Equaling to 0 equals to this goes this way about A. So that's minus 4 times the moment arm of 6. Now, this B produces a plus, and it's B cosine of 30 times a 2 and a 6, or an 8. I'll put the 8 right there. And so what you'll get is 24 divided by 8 cosine 30 is equal to B. Okay, I think, yes, I do have octave up. (24) divided by 8 cosine degree of 30, 3.46. 4641. Okay. Now, let's do something very interesting. I found both these from Summing the Moments. Let me just do this now. Sum of the forces in the y direction equals 0. We'll call that being positive. So I'll first take this one, then I'll take this one, and then I'll take that one. Okay, now minus 4, that's the first one, plus the ay, which actually I ended up with 1 right here, and then plus 3.4. I'm taking this one, 641, and I have to take it times the cosine of 30. And this all has to equal to 0, does it? This one now isn't a find thing. This is a check. So let's check this out. Let's see if... Okay. So obviously, let's take a look at what this number right here becomes. We want to look at what... Okay, so here's the way I'm going to do it. Since I know that's going to be the value, then I'm... Sorry. Times cosine degree of 30 gives me back a value of 3. So in fact, this value is in fact 3, and therefore 3 plus 1 minus 4 is in fact equal to 0. So this says it checked out. The B is actually that. That's correct. Is there any other way to find A except to just sum the forces in the X? We could work on the geometry here and find it off of this, but it might be that it takes a little bit more effort now that I've already gone this direction. So I might be more inclined to just say, all right, I'll just go and sum the forces in the X direction, this being positive, equals 0. I'll take the AX first, AX minus, and then I'll take the B right here over there, minus B sine of 30, and then say AX is equal to, and I'll take the B, put it in here. Hang on, whoops. Taking the B, putting in here, it'd be 3.4641 sine of 30. Okay. One 1.7321. 1.7321. Now, I am muting this as much as I can during the coughing. So here's the AX. Let's go back and take a look at something. If, just out of curiosity, AY is 1, AX is 1.7321. Yep. Okay. Okay, so got those two numbers. Now, the key here is kind of this. This was just a measured off of the assumption that everything was to scale. In other words, take this distance on the page, copy it 3 times, and it will work out. So I don't think this is to scale. But the key is if it was to scale, how could we find this out? If we found a location here, does this line go through it? Well, I don't know. Let's take this and let's see. Let's go ahead and actually find that angle based upon these two. I'll do this. 1.7321. So it says it's 60 degrees. I'm going to drop that last digit. Okay. So it's going to be a 60-30. So in fact, this will be 30. That'll be 60. Not that I really care that much about that, but what is the magnitude there? 7.321 squared 2. Okay, that sounds right. So that's a 2. So magnitude of 2. So if I were to draw this up here, and it was 30 degrees, exactly like what he's saying, and this is 6, how far up is this? Okay, so in other words, this is 30 degrees. That's 6. How far is that distance? Well, here, you could say 6 is to this, as this distance is to 1, or the distance is going to be, how about 6 divided by 1.7321, or 3.464. Now, let's look at it like this standpoint. Now, is at the same distance that you get from a triangle that sits like that. That is, say, 30 degrees there. Well, let's see. Tangent of 30 degrees is going to be, hang on, 30 degrees is going to be 0.57735. 0.57735. Make sure I wrote that down correctly. Yeah. Now, if I take 2 and run it up under, what do I get there? Don't know. I should have done 3.4641. So in fact, that's pretty much close to what I got there. So it does in fact cross right there. If you really wanted to find that geometry and go through this, you could solve it using geometry. Some people do that. I find it easier for me on a problem like this to just go through uh, the moments. So in review, first thing we did, we summed the moments about the right end. Second thing I did, sum the moments. I'm sorry, I summed the moments about B. Then, and this thing is probably not a good way to do it. The next thing I did is I summed the moments about A. After I did that, I decided to do a check, and the check was, let's compare what I would get if I just summed the forces about the Y. That came out as a check, and it said, okay, the value I got for A, Y, and B are okay. Next thing I did is I said, okay, I got to find the X reaction. So I did that with some of the forces in the X. Then I started playing around with the geometry here and trying to find, okay, recognizing that these things pass right here, I could have solved the problem that way, but it turns out, yes, in fact, this is what happens, that A has to pass through those points. 3 loads, they pass through there. Okay, let's go down. Okay. Apparently it will not let me do anything unless it's with my touch screen. It's okay, I guess. Okay, let's see. That seems interesting. But I can't get it to become small enough to grab it. Maybe if I do this. It can't be that big. I do not know what's happening here. Oh, it's delaying quite a bit. Jeez. Okay. Okay. Let's use our snippet tool. Okay. So instead of me drawing a free body diagram of this and spending the effort, I'm just going to put the forces on here. Okay, this surface of the flange has to put a force back this way. So it's a roller there. So I'll call it A, Y. That's it. This flange has to put a force back on this point B this way. This will be BY. And then, of course, this is already putting a force right here. It's 500 pounds. And that's pretty much it. So the sum of the moments about A, and I'll just take that. Okay, if you're summing the moments about A, that's this point right here. Then essentially this is going this way is equal to BY. The moment arm is 8. Okay. Then the next one is the 500 pounds goes this way, opposite direction of positive, and it is 500 pounds, because that's what it is, and it's 8, 9, 10, 11. I'm keeping them in inches, it doesn't matter. And that's it. So BY would be 500 times 11 over 8. Or 687.5. 687.5. Now, I want to sum the moments about point B. Okay, so I'm summing the moments about that point. So this one goes that way, and that is in the positive direction. That is AY, its moment arm. From B back to A is that 8 inches. And we're still summing about B, and this one goes this way. 500 pounds times that 3 inches is equal to AY is equal to 1500 divided by 8 equals to 187.5, 187.5. Okay, so I got my two answers, but I can check them. Sum of the forces in the y direction equal to 0. They must equal to 0. We'll consider this to be plus. So the first thing we're going to grab is minus AY plus BY minus 500. Well, I found those from before. I'll take the AY, put in here, minus 187.5, plus my BY, put right in here, 687.5, minus 500. Okay, I have no unknowns, but I have it checked. So let's check this out. Minus 187.5 plus 687.5 minus 500. And guess what? It equals 0. So in fact, this is a way to check this one and that one. What's the time? We're at the end of the time, so I think we'll just continue and do more of these next time.